Hey everyone, I'm Neil Patel. I want to talk to you today about my research proposal speaking on using liquid-impregnated surfaces that have been supplemented with essential oils to help reduce bacterial growth and infection rates in enteral feeding tubes. To start off, what I'm going to talk about first is, why is this technology important? What's sort of the need for it? And mainly I want to look at the background and sort of some of the risks associated with modern enteral feeding. So enteral feeding tubes, or EFTs as I'll refer to them, they can be used whenever traditional feeding is not feasible, sort of through the upper GI tract. This could be for structural issues, appetite or nutrition issues. These can be caused by any sort of, various diseases. And so this is a really common thing that's used. The most common is the gastrostomy tube, or G tube. It's implanted directly into the stomach with a port, and then the patient can use that port to administer nutrition or medication through that. Unfortunately, the infection rate in current EFTs can be as high as 40% in implanted cases. On one hand, this requires a complete surgical replacement, which of course is difficult, but also this infection can spread, throughout the body. And the most common site where you'll see these infections are right actually at the port itself. And so having access really to the internal body systems for that infection can lead to it to spread and be really harmful for patient outcomes. In the global EFT market, it is really significant. It's projected to reach about just over $3.5 billion US dollars by the year 2025. So this is a pretty high demand market, and so there is a lot of need for sort of improvement in this regard. What I want to talk about, what can improve these feeding tubes, is sort of the coating that's placed on them. Currently the infections, they start by bacteria growing and kind of adhering to the tube, and once they build up to a significant enough count, they can cause an infection that spreads. The bacteria has to stick to the surface of the tube for this to happen. And what the liquid impregnated surfaces, or LIS coating, can do, it basically takes a particular liquid and it spreads it over a textured solid that's applied on the surface. This increases non-wetting to a really high level. It's much higher than even traditional superhydrophobic surfaces, and ultimately it prevents bacteria from attaching to the surface as the liquid sort of spreads over that solid and creates that dynamic interaction over the two. That has to be considered anytime you talk about feeding tubes. They're used to deliver primarily nutrition. That includes things like fats, carbohydrates, but something really important to think about is it includes a lot of proteins. And proteins, due to sort of their partially hydrophobic, partially hydrophilic nature, they can adsorb to the surface of these EFTs and build up over time. And these proteins, as they kind of build up on the surface, provide binding spots for these bacteria that otherwise wouldn't be able to stick to the surface of the LIS coating. So something in this research proposal we have to think about is, will this coating prevent sort of this protein buildup and bacterial growth in that sense? Now, thinking about, what is the current technology and how can this research sort of improve upon that, I really want to take a look at uncoated EFTs. They currently don't have much to offer in the terms of antimicrobial resistance. Most current EFTs are made from one of two materials, either polydimethyl siloxane, or PDMS, or polyethylene glycol, PEG. These are often chosen just because they're very practical in terms of a manufacturing sense. They're affordable, they're easy to produce in large quantities, but the trade-off is that there isn't any significant resistance to that bacterial buildup. On the left, you can see the two structures of the repeat units for these polymers, and while the base tubes can still continue to be made from these materials, there's a lot that can be gained by having a coating that's applied on top of those. So thinking about, how can we use the LIS technology but also leverage additional, supplementation, essential oils have been studied for quite a bit of time, and they've really well known to have antimicrobial performance. The different mechanisms through which they act vary from oil to oil, but most of them contain phenol rings, and these can act as antioxidants, which kind of through this figure you can see they act on different parts of the bacterium and kind of disrupt bacterial function and kill off that bacteria. Ultimately, it prevents the bacterial concentration from reaching a point where infection is a risk. One of these things that we do need to consider for the LIS coating is if we're adding in the essential oils, we need to add it in at the proper concentration. If it's too low, you won't gain any of those positive properties that you're looking to implement. But if it's too high, they actually can go on and denature the sort of essential proteins that we're looking to deliver and kind of interfere with proper nutrition, in the patient itself. This research, how are we going to identify and develop that ideal coating, that it ticks off all the boxes we're looking to hit, as well as isn't, too difficult to produce. And really, we're going to have a lot of different coating candidates with, so many, almost 20 to start, 6 base oils in various concentrations. It's too many to quantitatively run lots of long experiments and break it down. We're going to have to start with what's called zone of inhibition studies. So these are essentially a qualitative study. Works to do 2 things at once. It's going to narrow down and let us identify quickly what's the top oils for the base that's going to give us the best performance, but also it'll help us identify what's the best concentration we want to supplement at. We want to look at 1%, 5%, and 10% by weight of the essential oil supplement in there. And essentially what we use is we use agar plates that will have a bacterial culture spread on them, and then we'll take coupons, made from either PDMS or PEG that have had both the Parylene C texture, which is a polymer that provides the solid layer, and then we'll add in the supplemented essential oil, so it'll be at that concentration in 50 CST silicone oil. And then we'll take those coated coupons and we'll press them into the bacterial bed. We'll let them incubate for 24 hours, and then what we're hoping to see is really this target outcome, where we see a huge kind of zone outside of that coupon where that antimicrobial property is sort of spreading throughout. So this will let us narrow down lots of those oils quickly and take us to, cut it in half, really, maybe around 10 or so to the next. So for the next 2 stages, we need to follow it up quantitatively. And then the 2 assays we're going to make use of are the XTT assay and then crystal violet quantification. The XTT assay, it makes use of a reduction mechanism in the mitochondria of bacteria to basically measure metabolic activity. And the more more metabolic activity there is, the culture medium will develop this richer and richer orange color. This assay can be repeated multiple times, which makes it really attractive as a choice, but it only measures live cells. So it doesn't paint a complete picture of how much bacteria is present really on the tubes. Crystal violet quantification, on the other hand, it stains. It uses a dye to measure any biomass that's there. So it measures both live and dead, but it is a terminal assay. So we can only run this once at the end of the study. And then those absorbance readings that we'll get from a UV vis scanner, we'll then convert those to a CFU count to really quantify how much bacteria is growing. Finally, it's 2 stages of quantitative assessment, or we want to continue narrowing down. We want to look at the performance in conditions that most mirror, real life when patients are going to use these feeding tubes. And the way that's going to have to be done is with underflow conditions. We need to start with static tests, which is segments of coated tubing that are immersed in the culture, but then finally move on to dynamic conditions where full-length tubes are subjected to flow at different rates, and we kind of account for all the different things that go into developing a coating that's both effective and safe. To summarize, we're going to start with about 18 coating candidates at different oils and different concentrations. We'll use zone of inhibition to qualitatively knock out, 50% of them, and then take static studies, break it down 5 to the 6 top performers, and then ultimately put that flow condition to use. Dynamic studies to get, the 1 to 2 best coating candidates. And sort of then we can move forward, take these formulations to further testing, animal studies, and then in vivo. And the goal really is to reduce the infection rate. You can't ever take it to 0, but I'd like to get it to under 15% from current 40. That's sort of what the industry is looking for. And finally, that technology, it represents a huge opportunity to take on a massive hurdle. And this market is growing very rapidly, almost a 6% CAGR year over year going into 2025. And so it's really important. It'll help save a lot of lives and, really impact a lot of patients' outcomes. So yeah, thank you so much for listening to this proposal. I really hope you learned something new and maybe you're interested in more. I'd love to take any questions you have. Thanks.